All right, everybody, welcome back. Monday, April 20th. Here we go. Moving into our last couple lectures here. I think we only have 5 actual lecture sessions left. So once again, keep sending in those questions. Make sure you take advantage of all 4 opportunities to get bonus points from those questions that you're sending in. We're going to start off today's lecture again with some great questions that came in from last week's lecture on Friday. We'll do a quick little review today, and then the amount of content we have to do is not that great. We'll briefly go over some exercise intensity and ventilation stuff specific to lactate generation and how breathing is actually partially regulated by the amount of lactate you're producing. Okay, which makes sense. And then we'll go into some of the anatomical components for pulmonary ventilation, some of the definitions. We get down in the weeds with kind of what each part of inspiration and expiration is called, but it's important to kind of understand those. You need to have the vocabulary if you want to be able to speak the language. And, hopefully we'll see if we can get down to spirometry today. I'm thinking that will be mostly part of Wednesday's lecture. As far as some small amounts of housekeeping, you'll probably notice that quiz number 3 was not posted. I delayed posting that until today. What you're going to do is that is going to be open until next Monday, which I believe is the 27th. Then exam number 3, which was originally scheduled for Friday, will be pushed off until Tuesday. That'll be open from Tuesday around 7 a.m. until Tuesday at midnight. So you'll have, once again, the whole day to work on that exam. And we'll pick back up with regular lectures on Wednesday. We have only 3 lectures for the cardiovascular section. So that is a very, very small little section at the end. And that is incorporated in kind of our cumulative final exam, which counts for the same as all the other exams. Homework number 3 should be graded and up hopefully by Wednesday, and then once again that quiz number 3 will be posted today, up for 1 week, and you'll have until next Monday at midnight to complete that. If you have any questions, need any other kind of allocations for time, just please get in touch. We got a lot of capacity for flexibility right now with teaching from home and everybody learning from home as well. So make sure if there are certain needs that you have, just get in touch and we'll make sure that everybody gets through this class. Okay? So I had some really, really good questions once again. Number 1, in regards to incremental exercise and oxygen consumption. That's that figure we drew at the end of the class. Okay? I'm going to zoom in on that in a minute. Does the decline in oxygen represent exhaustion or something else? We're talking about at the very end of exercise. If we stayed at that 12% grade and kept running presumably, with that intensity, would that line continue to decrease or would it stay leveled out? Meaning would it, plateau just at a lower value? Okay, well, let's zoom in. Here's our figure from last time, and the question is specifically in regards to that section right there. We've reached our VO2 max. We've gone up in elevation, so theoretically, the oxygen demand is higher. We need more ATP per unit time because we're exercising at a higher intensity. We're doing more work. More skeletal muscle contractions are required. So we would need more oxygen to supply that electron transport chain with the final electron acceptor. So at this point, we see this decline. What would happen if we kept going? Let's get our green pen back. The question is, would this, if we kept going at 12%, let's say we made this 12% here as well, would this line keep going like this? Or would, since it went to there, kind of just plateau at that lower value that's less than our VO2 max? And the point that our question brings up is, does this mark exhaustion? Not necessarily. What's going to happen is if you're able to keep going, and we have some pretty stubborn athletes out there who really don't like to quit when it gets to a VO2 max test, and they will keep going for a lot longer than you presume they're going to go, and any kind of difference between the VO2 max and wherever they are after the stage is going to be covered by anaerobic. Metabolism. And this is kind of similar to the concept we talked about last class about excess post-exercise oxygen consumption and oxygen debt that we incur at the beginning of exercise. This right here is almost a little bit of oxygen debt that's going to occur at the end of exercise. Okay, so think about if you run a hard 5K and you sprint in that last quarter mile. You run as hard as you possibly can. Now, if you just base the breathing that you do after the end of that race off of our last lecture, you'd say, oh, the reason that person is breathing hard is because they went into oxygen debt when they started exercising. Well, yes, that's true, but also you're going to further go into oxygen debt if you go above your aerobic capacity during that exercise. So if you go into like a little bit of a surge during one of your races, you're going to notice that your breathing goes up afterwards because you went into oxygen debt. Okay, so anything that's covered here is going to be that ATP that's needed is going to be covered by your anaerobic metabolism. And certain athletes have greater ability than others to kind of go above their VO2 max and actually run or cycle at a pace above that for a certain duration of time based on their anaerobic capacity. However, that does not change your VO2 max. And chances are you will not be able to make it 4 minutes past your VO2 max just by using your anaerobic metabolism. We know that in most cases, anaerobic metabolism kind of, if we're just going purely anaerobic, about 30 to 45 seconds, maybe 60 seconds if you're using some ATP PC. So great question there. The answer is, if we stayed at 12%, going with that intensity, would the line continue to decrease or would it stay leveled out? The answer to that is it kind of doesn't really matter. We've already reached our VO2 max. The important take home from that question is if you kept going and were able to keep going without exhaustion, any amount of ATP that is needed to maintain that higher level of exercise intensity is going to come from anaerobic metabolism. That's it, because we know we're not consuming more oxygen. And that's why that dip goes down a little bit, because your anaerobic starts adding in more than it was before. Okay, question number 2. Why do athletes wear, There we go. Why do athletes wear oxygen masks on the sidelines of competitions that take place at altitude? Okay, really, really good question. I've witnessed this before. You'll be watching like a Broncos game and you'll see, some team come in like the Jets or something like that. They're coming from sea level in New Jersey and they come to, Mile High Stadium and you see some of the guys on the sidelines with the oxygen masks on between plays. Why does that happen? And the thought is low partial pressure of O2 at altitude equals low HbO2 sat. So if you're coming from low altitude and the partial pressure of oxygen goes down because you're now at high altitude, remember on that curve, we're going to move a little bit to the left, meaning that our starting point for our oxygen saturation is not going to be the typical 98%. Okay, so by increasing the percentage in breathed in air, so if a person puts on that mask, and it's not just like a 21% solution, no, now we're breathing a solution that may be 50% oxygen or 100% oxygen, well, then the partial pressure of oxygen in your alveoli is going to go up. And theoretically, will increase your hemoglobin saturation. The problem that comes with this and where we see a divergence between the theory and what actually happens is most people, when they come to high altitude, their oxygen saturation isn't necessarily that low. So adding in this extra oxygen doesn't really do much to change their O2 sat. However, there is a big amount of placebo effect. Imagine if you come to a place like, Laramie or Denver or something like that, and you are out of breath, and somebody gives you a mask that is associated with your breathing. Do you think psychologically that's going to have an effect? Absolutely. So although we might not necessarily see a benefit during the event, there may be some psychological benefit as well. So a lot of times when athletes are taking oxygen on the sidelines, it's not going to do much for them. Sometimes it will. If their O2 sat is low, let's say they're at 90 and you have an O2 sat marker on your finger and you give them that extra oxygen, that's going to change it, okay? But we're not increasing the pressure, so it's not really going to increase any of your ability to transport oxygen after you take that mask off. So maybe for a little bit of recovery, it could help some people, but generally there's not much besides the psychological benefit. Okay, next. Does aerobic training allow someone to reach a steady state quicker compared to an untrained individual? If so, could this be used as an advantage? Okay, and the question there is, so remember, when we start our exercise, let's kind of zoom in here. If we have our O2 consumption there and our time, remember, when we start our exercise, we kind of have this gap until we reach this nice flat plateau. And the question is, if a person is trained, let's go back, let's do purple for untrained. And this is what theirs would look like. So it takes that long to reach plateau. What if a person was trained and they were going to exercise at the same intensity? Would they reach that plateau sooner? So between here and here. You can see when that line starts to straighten out there. So would it be faster for them to reach that? And the answer to that is not really. But with training, what you can do is you can reach a steady state at a higher intensity, a higher percentage of your max. So, whereas a person who is untrained, let's say we went up to an oxygen consumption that was way up here. And this person, okay, they're trying to get to that oxygen consumption, they're trying, kind of like that. Whereas a person who is trained is going to look more like that. So the timing is not necessarily different as when they're going to reach that. But in some cases, a person with training, they will be able to reach steady state at exercise intensities that an untrained person would not be able to do. Let's take Kipchoge, who's our 2-hour marathon runner. Okay, if he went out on the track and ran a 6-minute mile, he would be at steady state. Okay, he could run a 6-minute mile. Well, he could run under a 5-minute mile for more than 26 miles. But if you put me on the track next to him running that 6-minute mile pace, I am not going to be at steady state. I am going to be using a lot of anaerobic metabolism to supplement my oxygen consumption because I don't have the aerobic capacity to run multiple 6-minute miles in a row. Okay, whereas Kipchoge could run 6-minute miles probably for like 30 or 40 miles. He's an incredible athlete. You take somebody else like Gwen Jorgensen, who's a great triathlete and marathoner as well. She could probably do the same thing. You get out there, you're running a 6-minute pace. She could keep that up for a long time, whereas I'm not going to be able to do that. So the question: can aerobic training allow someone to reach steady state quicker compared to an untrained individual? I'm going to say the answer to that one is no. But you can reach steady state at exercise intensities that untrained can't reach. Can you use that as an advantage? Absolutely. Let's say you're running a 10K race. You can go out at a pace you know that your competitor cannot achieve, and you know that you can maintain that at a steady state where them trying to keep up with you is too challenging. Okay, last question. Oxygen debt, as far as oxygen debt at the beginning of exercise. I said that there would be no oxygen debt if you were just walking. So, is there no oxygen no gap in oxygen consumption and energy demand until you get to a higher exercise intensity. At what intensity does this gap and O2 debt start to occur? And you know what? I thought about this question a little bit more, and it turns out I'm probably a little bit off. But let's go back. Okay. Let's zoom in on this guy right here. Okay. So this is going to be our energy demand. And this will be our O2 supply. And what we basically said last time was, okay, you start exercising here. Oh, let's do this in blue because this is your O2 supply. You start exercising here, you get this kind of thing. And then you stop exercising and you get this kind of thing right here. Where this is the energy demand, looks like this, and then that. There we go into steady state, and then we don't need exercise, and that's our epoch at the end. Okay? So that's what we talked about last time. And we talked about running at 7 miles per hour. Now, let's do the same thing, but let's say you're going for a casual walk. We're going to start our exercise a little bit further. Actually, let's do this. Let's get rid of these guys just to kind of clear the picture. So now, we're just going to get up from your seat at the end of class, you know, like when we used to be able to go to class, and you're going to walk out of the room. Same thing's going to happen. You're going to have O2 supply that kind of, let's say, looks like this. And then you'll have energy demand that looks like this. Oops. So last time I said, hey, there'd be no, kind of oxygen debt there. But the real thought is, it's just super, super tiny. Okay? So yes, when you first get up from your chair, you're going to use stored ATP to enable yourself to get out of that chair. When you get out of that chair, as soon as you start walking, you're going to perceivably be able to counteract that oxygen debt while you're exercising to help, you're exercising and you can regenerate that oxygen while you're doing it. So afterwards, you're going to have only a really tiny epoch as well. So the answer to that one is, does oxygen debt only start to occur once you get to higher exercise intensities? Not theoretically. There's going to be a small amount of oxygen debt, but the degree of it is so small that you don't really need to sit down after you go for a gentle walk across campus and catch your breath. When we're talking about oxygen debt and epoch, we're really talking about that heavy breathing that's associated with following exercise. Okay? So hopefully those answer some of your guys' questions. Let's go through a quick little review and then we'll get into the new content here. Okay, what fuel source is used to supply energy during the early stages of exercise? Aha, we just covered that. Fantastic. Anaerobic. So we'd be using carbohydrates. Great. How does this relate to the name of this period of oxygen consumption, energy demand, and balance? Well, we called it oxygen deficit or oxygen debt. And the reason that these are related is because of, look at this. We think about this anaerobic. Anaerobic means without oxygen overall. So that's how the name relates to what we're talking about in those early stages of exercise. Remember, you're taking out that loan from your anaerobic metabolism with the promise that after you stop exercising, you will continue to breathe at a higher level than you need in order to bring that oxygen back to your skeletal muscle and help to regenerate some of that anaerobic ATP that you used. Okay? Number 2, what is epoch and what good is it anyways? So the question is, let's define that. That's excess post exercise oxygen consumption. And what good is it? Well, we just talked about what it does. Helps to replenish anaerobic metabolism. Just as we discussed a minute ago, if you didn't have your excess post-exercise oxygen consumption, you wouldn't be able to start exercising at a high intensity. Basically, what you would need to do is you'd go back to your figure from above, right? This one right here. And you'd be only able to slowly increase your exercise intensity. You wouldn't be able to step onto a treadmill and run at 7 miles per hour. You'd have to start walking and then slowly start to increase and slowly start to increase. You'd have to always max your exercise capacity with your ability to consume oxygen, okay? And that takes time, as we know. We talked about the different neurogenic factors that are related to that. So if you didn't have excess post-exercise oxygen consumption, you wouldn't be able to start exercising at a higher level immediately. Okay. Last one, how will the oxygen consumption curve during a stage of graded exercise differ between stages of relatively low intensity versus stages near maximal intensity? All we need to say there, let's say here's our stage. Here's our early stage. Look at that. Long plateau right there. Okay, here's our same time point. Here's our late stage. Short or no plateau. Okay? So as we get towards our end stage, remember, we're not able to match our oxygen consumption with our energy needs, and therefore we are going to just keep on breathing more and more and more over that whole stage. You might be able to complete it, but you won't necessarily reach that steady state. Whereas in early stages, you will definitely be able to reach that steady state. Okay, let's move on to some new material for today. This is kind of one of my favorite little things to teach me about how oxygen and breathing is related to ATP. Okay, so we want to describe what happens to gas exchange when we exercise. This is a cascade of events. So we are exercising. We're going to get on that elliptical. We're going to knock out our 30 minutes like we do every day. Really important, especially when we're kind of homebound right now, to get that cardio in. So we have increased demand for ATP to power that muscular contraction when you start exercising. All right, well, then if you increase the ATP need, then you increase the oxygen need to act as that electron acceptor in the electron transport chain. We need more ATP, we need more electrons going through the electron transport chain, and therefore we need more oxygen to get those electrons out of the electron transport chain so another NADH can donate some more electrons. Okay, well, then if we need more oxygen, we need to increase the amount of oxygen transport from the alveoli to the blood. We need to pull that in more. Well, if you're doing that, then you also need to increase the carbon dioxide that is off breathing from carbon dioxide. Well, if you need more oxygen to get onto the hemoglobin and you need more carbon dioxide getting off the hemoglobin, the end result to that is you need more ventilation. You need to breathe more. If you don't breathe more when you start exercising, you will not be able to supply the increased amount of ATP that is in demand. And the reason that you need to breathe more is because you need more oxygen and you need to get rid of more carbon dioxide. So let's see how that relates overall to our lactate threshold. So what we're going to do down here is we're going to draw a little picture. And at 0.5, this is our oxygen consumption on the bottom. Okay, and this is going to be in liters per minute. Okay, and then on our first y-axis, we're going to do ventilation. And let's do, we'll do this one in black. Okay, how much air you're moving. And this is liters per minute. Okay, and for scientific notation, this is just liters times minute raised to the -1 power right over here. Sometimes when you're writing for journals, that's the way you'll put it. Instead of doing liters over a minute, you'll multiply it by the negative, by the inverse, okay? Just so you know what's going on there. And you'll see, look at this. I mean, we have hundreds of liters of air moving into and out of the lungs per minute, but we're still only consuming a couple liters of oxygen per minute. So our other y-axis over here on the other side, this is going to be, we'll do this guy in red, and this is going to be our lactate. And we'll put the brackets for concentration, and this is going to be millimoles per liter. Okay, so we got our figure all set up. And what we're going to do first is we're going to talk about lactate, because we've covered this before. You guys know what happens to lactate. And we're going to start right here at rest. And at rest, we have a very, very low lactate concentration overall. Let's even go down a little bit lower. We know we're not even at 1, because 1's going to be our lactate threshold. So here we are. Here we are at rest. We have a little bit of lactate. Let's say, 0.5 millimoles of lactate in your body right now. Okay. So as you start exercising, this is going to be, let's put these things in here. This is rest. This is going to be some light exercise. Then if we move on, let's go to like 2. We're going to call this like moderate, MOD for moderate. And then if we move to like 3.5, we'll say that's high intensity. If we're running very hard when we're getting to 3.5 liters per minute of oxygen being consumed. Okay, so let's go back to our red for lactate. What happens to that lactate concentration as we start to exercise? Go from rest to 1 liter per minute. Not too much. Remember, you're able to oxidize enough to get rid of that. So there's no real problem there. But then as we start to move towards moderate exercise, we start to see a rise. Just like that. And when we get to moderate, oh, we're right about here. Well, right about here. We have now reached our lactate threshold. Remember that, okay? So that's that first one. And then we also had our 4, which was our onset of blood lactate accumulation, right? So we know that our lactate is going to kind of keep going up from that point right there. And then when we hit this point here, we're going to get another change. That'll go just like that. So we have these kind of 2 breakpoints. We get this nice kind of slow rise. We get this line right here. Okay, and then we get that breakpoint. So we have 2 breakpoints in our lactate curve. All right, and remember, we said as our exercise intensity increases, we also need to get more air in. So how's that going to change? Well, if we go back to our ventilation, let's start at rest. We're right around here. And remember, as you start exercising, we have a more linear relationship with our ventilation. It's a lot better than our lactate is, or a lot more clear, because with lactate, remember, we're able to get rid of some of it and oxidize without that concentration rising. But with ventilation, as that exercise intensity increases, we're absolutely going to need to ventilate more, and the reason that relationship is there is because of tidal volume and breathing frequency. All these additions we've gotten here in the beginning, that's probably going to be mostly due to tidal volume. You're not breathing that hard at that point. However, once you reach that lactate threshold, whoa, your body says, hey, I need more oxygen here because my lactate concentration has obviously changed. And at this point, you're going to get a break in your breathing. And it goes right to about here. Let's undo that one. Look at that. So you can see we have a break there as well. And then again, when you hit your lactate or your onset of blood lactate accumulation, Once again, that's another signal to say we are not supplying enough oxygen. If we were, we would be able to oxidize all of this lactate. So if we're not getting enough, guess what? We're going to get another break line. Just like so. And you can see the slope of those lines change right along the same kind of plane. Okay? This point, this first point, is our ventilatory threshold. And the second point right here is our respiratory compensation. Okay? Ventilatory threshold happens along with your lactate threshold. Respiratory compensation happens along with your onset of blood lactate accumulation. All right? And the reason that this kind of happens is because if we think about this reaction, let's zoom in here. Let's do this guy and that. And let's think about lactic acid. Remember, we're going to react into our sodium bicarbonate right there. And then, let me just zoom in on my old notes. If you combine, sorry, not, that's my problem. If we combine our lactic acid with our sodium bicarbonate, okay, let's say, for example, you took some baking soda beforehand, what that can do is it will produce sodium lactate plus H2CO3. Our carbonic acid, which can then break down into H2O plus carbon dioxide. Well, if we have more carbon dioxide here, we're going to have an increased partial pressure of CO2. If we have that increased partial pressure of CO2, you're going to need to breathe more to get that carbon dioxide off. So that's what we're basically showing here, is at these points that we've kind of predetermined as being break points in these curves, well, as that lactate concentration starts to kick up faster, your breathing is immediately able to compensate for that by increasing your ventilation and increasing your respirations right there. So let's just give a couple quick little definitions at the end. Ventilatory threshold is the point where pulmonary ventilation increases disproportionately relative to increases in oxygen consumption. So if this was able to continue proportionately, let's erase some of these lines in here. Basically, what we would see is this would keep going like that. But this is that disproportion right here because we've changed the angle of gain. So it's disproportionately right there, okay? Relative to increases in oxygen consumption. Increased breathing due to increased carbon dioxide offloading due to lactate buffering. That's what we just said in that equation above, okay? We're offloading that carbon dioxide because we're producing more of it. Okay? And there's some in that lactate that's being broken down as well. Respiratory compensation at the end of exercise, that increased breathing rate is necessary during high-intensity exercise as a mechanism to increase our alveolar PO2. So whereas we're breathing more in the early stages of exercise at that lactate threshold, the reason that is occurring is because your partial pressure of CO2 is too high. Now, towards the end of exercise, we need to increase our alveolar partial pressure of oxygen to get more oxygen in and decrease that partial pressure of CO2. So ventilatory threshold is primarily due to just CO2, whereas respiratory compensation is due to both CO2 and oxygen. Okay? Important to remember. So, if you remember back to a few lectures ago, probably our first lecture in the respiratory component, we showed this little figure right here. But I had blocked this section out because I used it for a different purpose, basically to show the difference between the conducting system, your anatomical dead space, and some of the different volumes of those areas overall. Now what we're doing is we're going to be using it to talk about the difference in the numbers and the cross-sectional areas. So we talked about the volume before, but the more important thing here is this last point that I'll highlight right here. The cross-sectional area of our alveoli is, orders of magnitude higher than the cross-sectional area of your bronchioles. And the reason that I'm bringing that up and the importance of that is that allows for that gas transfer to occur. So what you need to remember from this one is that as we descend down our conducting system and into the exchange surface, the diameter goes way down, 1 to 10 millimeters down to 0.3. The number goes way up exponentially, and therefore, because of that, the surface area goes up. And if the surface area goes up, our ability to transport gas from one area into another goes up as well. So, the last thing I wanted to cover for today was this picture right here. And this refers to some of our different areas of breathing. And this is the vocabulary that I was talking about before. What we're doing here, this is our let's make this a little bit bigger so you can actually see it. This is our casual breathing, okay? Then we're going to take a big inhalation. Then we're going to breathe out as much as we possibly can after that big inhalation. And then we're just going to go back to our normal breathing. Each little section of this figure has a name, okay? And we've already covered a couple of these. The first one, though, that I want to cover is right here, and this is our tidal volume. And what we'll do is right down here, we have the numbers. So we have number 1. Here's number 1. And that's tidal volume. And then I'll just give a definition and give just an approximate value that you guys can use kind of as a reference point. So the volume of one breath, inhale and exhale, because you can see this line goes up and down, right? One breath at rest. And we've already covered this. We know that the volume of about one breath at rest is around 500 mLs. Okay, let's move on to number 2. So now, if we follow this line right now, we are here. What is happening in this region right here? Well, we are inhaling, so that is our inspiratory reserve volume. So you're breathing normally, and this would be the, that's what your inspiratory reserve volume is. So let's move down to our number 2 and define. And this is our max inhalation after a tidal volume inhale. So we've already done our tidal volume, and then we just go more. Okay? And the normal amount of that volume right there is going to be about 2,500 ml. And that makes sense, because if you breathe in all the way, that's a lot more than you normally breathe in. Okay? Now, let's go to the next section. And that is going to be, we're breathing out, we go past our tidal volume, and now we go into our negative zone. You breathe out more than you normally would. This is our expiratory reserve volume. That's going to be our number 3 right there. Our expiratory reserve volume is your max exhalation after a tidal volume exhale. But the big thing you'll notice here is this is a lot less than our inspiratory reserve volume. We only have about an extra 1,000 mLs or an extra liter to breathe off. Okay? But we've passed over a couple boxes here, and number 4 is right here. So after you breathe out as much as you can, is there still air in your lungs? Absolutely. If there wasn't, your alveoli would be flat like that. It would be very hard to get air back in there, and that would be a bad thing. Think about when we did our underwater weighing. Remember, we subtracted what we called our residual lung volume. That's what that space is right there. So is there still volume left in your lungs? Yes. Can it functionally be used? No. Okay? So number 4 is the volume in lungs after a max exhale. And the volume there is going to be about 1,000 milliliters as well. And these are all just approximates, okay? Depending on a person's size, these values are drastically going to change. But I just want to give you some reference between these, which one's kind of bigger than the other one in general, okay? Last one, number 5, up here is our functional residual capacity. And although I said that residual area is not functional, this area right here is functional because we are kind of using that, so we want to be able to make sure that we have that. So if we had to define number 5 right here, this is the volume in the lungs after a tidal exhale. And if we wanted to figure this out, well, this is just number 3 plus number 4, right? It's this space plus this space. So if we wanted to add those up, it's this plus this. So it's going to be about 2,000 mLs. Okay, moving along. 3 little boxes left to check here. And now we are on to number 6. If we said the total amount that went down this way was our residual capacity, now we're going the other way. This total amount that we can go from a normal exhale is going to be your inspiratory capacity. There we go. Number 6. And this is the volume, max inhalation after, or it's your max inhalation volume. From rest. So if I just basically said to you, you know, sitting there right now, okay, take the biggest inhale you can, you'd just be able to go, that would be it. But if you want, and the volume for that is about, let's see, 3,000 mLs. Okay? Because it's our 500 plus our 2,500 right there, right? But if you really wanted to breathe in as much as possible, well, the first thing you would do is breathe out. And you probably wouldn't get much higher, but you would have more air passing by your mouth. So if we wanted to define that one right here, this would be our forced vital capacity. Forced vital capacity. You've probably heard of your FVC before, and you definitely will if you take some of our other exercise physiology classes, like Dr. Smith's class or any of Dr. Brunn's classes. You'll probably find out about that one a little bit more. But for this, we just want to define it as the max volume inhaled after 1, 2, and 3 happen. After, and we can just say a max exhale. And the FVC is really helpful, and this is where we talked about spirometry before, because we can use the dynamics of this FVC to be able to start diagnosing certain illnesses overall. And so we know that's about 4,000 mLs, because we know we had about 1,000 mLs for our max exhale, plus our 3,000 for our max inhale equals 4,000. But if we want to kind of put a bow on this and put it all together right here, we have our total lung capacity. And the way I explain this is if you were basically to take your lungs out and fill them with as much air as they could possibly hold, that would be your total lung capacity. Okay? Total volume in lungs after a max inhale. Yep. And that's going to be about 5 liters total. Okay? So that would be if you're breathing really, really hard during high levels of exercise. One breath could potentially move in about 5,000 ml or 5 liters of air. Okay? And we have the capacity to do that right there. We're going to move on. This is where we're going to be talking about our forced vital capacity, but I want to wait until Wednesday for that lecture. I want to just stop here for today. Keep those questions coming. You should see the quiz being posted hopefully pretty soon this afternoon. If you have any questions about the exam or quiz, make sure to get in touch. All right, see you guys on Wednesday.